Alright, we're back at it. Again, these PowerPoints are made by John Frensley at Frensley AP Physics. There's a Facebook page if you want to follow that. Essential question. Last time the essential question was, how do we communicate the object's motion? This time we're going to take that same essential question, but we're going to make it a little bit better. Finally, we're going to add so that we can make predictions, which is a really powerful thing to have. So we're going to be able to interpret the motion of an object from a table, and then we're going to take that table and turn it into a motion diagram and interpret that. And we're going to be able to write an equation of motion, interpret one, and use one to predict the future. Then finally, we're going to be able to create or interpret a graph of motion, change it from one type of graph to another to show the same motion. There's your pages for OpenStax. If you would like to read, I definitely suggest that you do to follow along. Alright, vocabulary. Same vocabulary as last time. We have our motion diagrams, which were the strobe, 1 second intervals to show the motion. If there's equal spacing between the motions, then we knew that that was moving at a constant velocity. Slope of a graph is the ratio of vertical to the horizontal change, so it's rise over run, the y2 minus y1 over x2 minus x1. Area of a graph, the area by the graph line or curve. The horizontal axis and the two vertical lines called the initial and final. We'll talk more about that and you'll be able to see it. If you did the calculus, then you know that it's the integral. Why do we need to learn this? Last time we discussed how we can communicate motions with our communications. We can explain what happened when an object moved. Physics is about more than what happened. Specifically, physics is about communicating what happened, what is happening, and being able to predict what will happen. People pay frauds with crystal balls lots of money to predict the future. Meanwhile, we physicists use scientists to actually predict what's going to happen. We can communicate motion the following ways. Some are easier to use than others, depending on circumstance. We have a table of motion, motion diagram, motion equation, motion graph. So any one of those is going to effectively communicate what's happening in a given situation. Ultimately, though, we want to have a nice, robust combination, including, I would add a dot in there, that we need to have a narration of what's going on. So you have to be able to take a graph and turn that graph into words, which is a skill we'll be working on for the next little bit. Tables of motion, easy to make, hard to use, right? So a table of motion can be a position and timetable or velocity and timetable. It tells us where the object is at different clock times. Position is positive if the object is to the right of the origin, or negative if it's to the left or below the origin. Velocity and timetable tells us how fast an object is going at different clock times. Velocity is positive if the object is moving to the right or upwards, and negative if the object is moving left or downwards. That's tricky. A lot of students assume that a negative velocity means that you're slowing down. It's not. That negative, remember, is just the direction that we're going. So here we go. With an example, position and timetable. We can see time is equally spaced out here, so we know it's every 2 seconds. We've seen those before in the last slideshow. Here's an example, and then we can, just by looking at this, we know it's going 5. So the interval here is 5, the interval here is 15, the interval here is 25. Looks like we're speeding up. Note the times are equally spaced. The distance becomes farther apart as it increases. 0 to 5, 5 to 10. That's because the object is speeding up, because it travels more distance in equal time intervals. This position shows the exact same motion as the last one. This time the positions are regularly spaced, but the times are not. The times become closer together, so 0, 3 seconds, then 1 second, then 1 second and change, then less than 1 second, and then less than 1 second. So the times are becoming closer together. The last two are 0.51 seconds apart. That means the object is speeding up because it travels the same distance in shorter intervals of time. How do we calculate average velocity? Well, average velocity is displacement divided by time interval, right? E equals delta x over delta t. The change in position for this whole table is 36 meters. 50.3 minus 14.3. Remember, that is our final... Oh, we're not talking about velocity, we're talking about position. Our final position minus our initial position. Our final... Zoom out. Final position. Minus the initial position, which was 50, whatever, 50.3 minus 14.3. Was that so hard? Alright. Let's go ahead and zoom back out. How do we calculate an average velocity from the table? The change in position is 36, the time interval is 2 seconds, final minus initial. Dividing these gives us 18 meters per second for the average. That's it. So for an average velocity, we're going to take the whole thing. We're going to take the final. We're going to take the beginning. If we're looking for an average velocity between 1.5 seconds and 2.5 seconds, then this is our final. This is our initial. It's going to be final this minus initial this. Divide them, and then there's your average velocity. And how do we approximate an instantaneous velocity from the table? Suppose we want the velocity right at 3 seconds. Okay, we're going to go to 3. Oh, 3 seconds isn't on our table. So we're going to look at the two that are around 3 seconds. The change in position is 4.4 meters, and the time interval is 0.2 seconds. Dividing these will give us 22 meters per second at exactly 3 seconds, which is pretty cool. Here's an example of velocity and time. It's much easier to see the object speeds up, right? 0, 5, 10, 15 are the time intervals, and then the velocity 4, 3, 1, half. Each velocity is shown instantaneous velocity at the same time. Velocity is parallel. Problem is that finding displacement is pretty difficult. So we can't readily go between these two tables. We can only find displacement between adjacent points on the table. Displacement is your average velocity times time, v equals d over t. To find displacement between two adjacent pairs, we're going to multiply the average of the two velocities by the difference in the two times. So there's our time interval average speed and the displacement. We can only find displacement between adjacent points on the table. Can't help but feel like we just did that.